And of course, we want to make sure that we thank our presenter today, Alan Scott, FAIA. He's a fellow of our state and institute. Um, I have a brief bio I want to share with you, so I'll stop while so he can prep his presentation about Alan. But before I get to that, I'll just say Alan is also just a delight to serve with on a national level. He attends, and pays attention to a lot of things about this area of expertise on behalf of the full membership. So it's really a great resource for the state. Alan is a registered architect and a sustainability practitioner with over 35 years of experience as a facilitator, consultant, and teacher in support of high performance, sustainable, resilient built environment projects. He is the Director of Sustainability for Intertech Building Science Solutions, and Alan currently serves as Vice Chair of the USGBC Resilience Work Group with AIA, and as a member of the AIA, or excuse me, with USGBC, and as a member of the AIA Resilience and Adaptation Advisory Group, which I'm also a part of, and the USGBC Lead Environmental Quality Technical Advisory Group. He's busy, and today he is going to share some time with us to present on this topic. So welcome, Alan, and thank you very much.
Excited to be here with all of you. I feel lucky on this Friday the 13th to be with all of you and talking about the subject I care a lot about, resilience. Today, I'm going to be building on the foundations that Jay Raskin built for us last week, telling us about one of the key resilience issues we have here in Oregon with the Cascadia subduction zone earthquake and talking about public policy around resilience. So I want to build on that and cover some general definitions of defining what does resilience mean in the case of the built environment, what are some of the both regulations and trends that are pushing us towards consideration of resilience, and then quickly move in and actually do a deeper dive on specifics around wind and water and heat in terms of resilience responses in our design of and operation of buildings. So without further ado, let's dive in. Make sure that my slides are... There we go. So disaster movies are fun and interesting, and they may serve to raise our awareness about natural hazards and climate change. But the sensationalism of them also might make them seem less real in terms of a significant threat or risk to us, and so they may just desensitize us to the real threats that we face. So I just wanted to kind of use that as a start for the conversation about talking about what are the real risks that we face. I also think in this discussion that words matter. A lot of people talk about disasters, and a disaster to me implies something that is unanticipated and or unexpected. Actually credit Jay Raskin for sharing with me the importance of thinking about the word hazard instead, because hazard implies something that can be anticipated and prepared for to prevent it from becoming a disaster. So a disaster is a hazard you did not prepare for. Thank you, Jay, for that clever line. And disasters are becoming more, or disasters that could become, or hazards that could become disasters are becoming more prevalent. The world is getting hotter and drier, and at times wetter and windier due to climate change. And so the hazards that we faced in the past are getting more frequent and more severe. And this data from the National Oceanographic and Atmospheric Administration kind of makes that picture very clear. The trend is undeniable. Last year, we set a record for 25 major disasters with losses of $1 billion or more, so some of them much more. And as of the beginning of this month, we'd already hit 20 such billion-dollar-plus disasters for this year, and that doesn't include Hurricane Francine and a couple major wildfires that are currently burning. So by the end of this month, when they update the tally, unfortunately, that number is going to be ticking up for this year as well. The key message here that I want to share is past is not prologue. We need to be thinking forward about the greater risks from hazard events that we're facing in the future as opposed to what we're used to in the past. Kind of addressing this, many of you may remember in 2019, the AIA announced their climate action plan, which reinforced the commitment that architects should have towards sustainability and resilience, and talking about the necessity of designing for the effects of climate change. And so this is very much part of our responsibility, our professional responsibility as architects. One of the things that people often get confused by is code. Building code is not the same thing as resilience. I think about building codes the way I think about the frames on modern automobiles. They are designed with crumple zones in the frame so that in a collision, that frame absorbs the impact of the collision, sparing the occupants the worst of the impact. But afterwards, the occupants hopefully will walk away or be only sustain minor injuries, but the car is totaled and needs to be replaced. And so code is a minimum life safety standard, not necessarily focused on resilience to the ability to continue operating after hazard events. When I think about resilience, I think about it in sort of three aspects that are important in buildings. The bottom line, starting with building safety and security, about keeping occupants safe during and immediately after a hazard event. So building codes do some of this, but not necessarily far enough relative to all hazard types. So there's an element of immediate safety and security, but building integrity is also part of this, that we want to design buildings so that they can resist damage and or sustain minimal damage and go back into service quickly without having to be rebuilt significantly. And finally, in many cases, building functionality is important, and having a building that's out of commission for a long period of time is not necessarily it can be damaging to a business or a community service. One example of this, I'm actually looking at a hospital in Dubai that this last April was flooded out by the extreme rainfall that they have. That was unusual. The entire ground floor of the hospital was flooded, and that hospital 6 months later is still out of commission, pending repairs to get it back. And so 6 months without a hospital running is both a drag on the community in terms of a critical service, as well as a financial impact on that institution. Investing in resilience pays. The National Institute of Building Sciences estimates that for every dollar invested in resilience, you save $4 to $11 or more after a hazard event in terms of avoided losses. So there is a return on investment from thinking upfront about making resilience measures in our built environment. And that's both public investment in infrastructure and community, as well as individual investments in individual buildings. The other thing that I think is important to note, although it hasn't necessarily filtered down to conversations that we have with individual clients, there are significant trends happening that are going to be pushing all of us to be thinking about resilience in the built environment, if not now, in the near future. Banks are beginning to look at resilience risks associated with projects that they lend on. Insurance companies are beginning to look at not just blanket regional hazard estimates, but individual properties in terms of their risk, in terms of whether or not they underwrite insurance for those properties, or how much that insurance will cost. And maybe most importantly, real estate financial investors are beginning to look at the long-term risks associated with their investments in commercial real estate relative to the impacts of natural hazards and climate change. And so the ability to get projects funded and insured is going to be dependent upon how resilient are they, or what are the risks associated with particular properties and particular locations. The Securities and Exchange Commission has some rules around disclosure, not just of carbon emissions, but also of climate-related risks. California passed Senate Bill 261 a year ago that, when it goes into effect in a couple of years, will require all companies, public and private, doing business in California over a certain size to be reporting their climate-related financial risks, which in some cases have to do with supply chains and things like that. They're kind of outside of our purview as architects, but in some cases that those risks are associated with risks to individual real estate assets, which we have a hand in designing resilience for. Additionally, some volunteer standards like the ASTM is developing a property resilience guide, which I'll talk about, and the U.S. Green Building Council is integrating resilience requirements into LEED version 5. And I'll touch on a few examples of that as we go through today. The ASTM is on the verge of releasing the standard guide for property resilience assessment, or commonly now being called a PRA. It might go along with a property condition assessment, or PCA. And so we can anticipate this coming out. This property resilience assessment process is divided into 3 stages. And I want to just kind of briefly introduce you to those so you understand what kinds of measures people are going to be applying to buildings that you design later on when they change hands in a real estate transaction process. And this process can also be used to look at properties that are going to be developed in a pre-development phase to identify risks that might be integrated into a resilience program for a building you're about to design. The first stage is looking at hazard screening, so identifying what are the current natural hazards and future climate-related hazards that might impact a particular location. So this could be, current hazards like earthquakes, floods, tornadoes, hurricanes, as well as future climate hazards like sea level rise and drought, extreme heat, extreme rainfall, things like that that we can anticipate through climate models are coming. Just one note I'll make that's kind of an interesting comparison. The Southeast United States, Florida, and the Carolinas, for example, are already experiencing significant coastal erosion due to sea level rise. And that's partially because it's exacerbated by the land sinking because of, in many cases, overpumping of groundwater for agricultural uses. So sea level rise is happening at the same time that land is sinking, and it's exacerbating the problem. I understand that we have actually the opposite thing happening here in the Pacific Northwest. The Cascadia subduction zone, which Jay talked about last week, is actually causing the Oregon coast to rise more or less at the rate that sea level rise is happening. So until that big earthquake happens, we might stay ahead of sea level rise here, but we're going to be in trouble with the subsidence after the earthquake happens. When doing that hazard screening, there are publicly available tools like the FEMA's National Risk Index and other resources to help with those assessments. And there are also some proprietary tools that help put it all together. And so that assessment looks at qualitatively what are the high, moderate, and high hazard risks of different current hazards, and also uses climate models through the representative concentration pathways for carbon emission reduction or carbon emissions, determine potential for things like extreme heat, rainfall, drought, and sea level rise. The second stage of that assessment looks at vulnerability, and so vulnerability combined with the frequency and intensity of potential hazards is how you figure out the risk associated with those hazards for a specific location. The factors that when we look at vulnerability, we look at the vulnerability of both the asset and the occupants of the building, and not just the building itself. And the factors that go into that include exposure, sensitivity, and adaptive capacity. And just to quickly dig into what those terms mean. Exposure is what it sounds like. How exposed is that particular location, the building or site, to the identified hazards? And an easy example of this is that a waterfront property has greater exposure to a hurricane than one that's located a mile inland. So that changes the exposure. And interesting when we think about sensitivity and adaptive capacity, that has more to do with the type of facility we're talking about and the occupants who will be in that facility. And a quick way to contrast that is thinking about maybe your own architecture firm. If you have your critical project documents saved on the cloud or in an offsite location, and your staff is able to work remote on laptops, then if there's a hazard that affects your office, you can adapt and continue operating effectively elsewhere while the building is repaired. Where, by contrast, a assisted living facility with vulnerable elderly population, maybe some of them also in memory care, if the power goes out, there's extreme heat event, other things like that, you can't really move those people around to other places and keep them safe. So there's a greater vulnerability or sensitivity of that population to hazard events that might need to be considered in terms of resilience planning and risk reduction. The third stage of that assessment is looking at risk mitigation. So identifying of the given hazards and the vulnerability to those hazards, the risks associated with those, what are the physical and operational measures that can be put in place to reduce those risks? And that could be things like flood barriers that can be deployed, impact-resistant glazing in high wind events, having a photovoltaic system and battery backup for backup power, so that you have some continuity of operation, installing more wind-resistant roofing to prevent from the severe losses from roof blowing off, having high efficiency filters to take care of wildfire smoke, or simple things like drought tolerant landscaping and water efficient fixtures, so that in a water shortage scenario that there's resilience there. One critical thing in consideration about resilience is that it goes hand in hand with sustainability. So sustainability and resilience are two sides of one coin. Sometimes in the ESG space, this is referred to as double materiality. So when we're looking at climate-related risks, we look at transitional risks, which are risks associated with what you're building or your business is doing to Mother Nature, and physical risks, what's Mother Nature doing to your building or your business. And so there's regulatory aspects about transitional risks that are happening that need to be addressed, things like building performance standards that are setting caps on the carbon emissions from buildings in certain municipalities. And then physical risks, again, are looking at things like natural hazards and climate change and those impacts on a building. I mentioned the voluntary standards as well, and I've been working with the U.S. Green Building Council and integrating resilience into LEED version 5, which will be released next year. One of the key elements in that is that both for LEED operation and maintenance of existing buildings and LEED for new construction, there will be a prerequisite for conducting a resilience assessment in the case of new construction or major renovation prior to developing the project. So identifying what are the hazards, the primary hazards that the building will be subjected to, and addressing, how will those be addressed in the design of the project. So that's going to be a prerequisite in the new version of LEED. There are also, and I'll share a few examples throughout this next 40 minutes of where resilience measures are going to be sprinkled into prerequisites and credits throughout the rating system. Now, shifting in and starting to talk more specifically about hazards that we need to address with resilience measures, it's important to understand that we're not just talking about one hazard at a time, but in many cases, there are multi-hazard events. So there's a primary hazard and a secondary hazard. Primary hazard like wildfires that affect a specific location, and then wildfire smoke that impacts a much broader area. One thing to note is that secondary and tertiary hazards can be separated spatially and temporarily from the initial hazards. And one interesting example of that came up this year is down in New Mexico. 2 years ago, wildfire in the mountains of northern New Mexico left a burn scar on the hills. This spring, a heavy, unusually heavy rainstorm came through, caused mudslides in that burn scar that went into the water supply for Las Vegas, New Mexico. And so because of a wildfire 2 years ago and an extreme rainfall event that you wouldn't think would cause a drought, the city was out of water and had to shut down businesses and essentially was in a crisis mode because of their water supply being vulnerable and not resilient to those hazards. Another way to think about that is that hazards are often cascading and compounding from one another. For example, an extreme drought is something that can be an acute hazards that we're facing with. Sometimes those droughts occur in conjunction with heat waves. And in those kinds of scenarios, there could be an increased demand for electricity. At the same time, there's reduced water supply, which means that thermal electric plants that rely on water for cooling might need to shut down. That's happened several times in France over the last few years, where they had deadly heat waves because their nuclear plants had to be shut down in the face of a drought and extreme heat event. Extreme heat events in the summertime can also spawn severe storms with lightning or winds that can knock branches onto power lines, which then spawn wildfires and create wildfire smoke. At the same time, we might have power outages where we can't cool our buildings without opening the windows. So you can see that one hazard can lead to another, and impacts can be widespread and interconnected. One final note before we dive into the other details, not a day goes by, I don't think, that I hear about our shortage of housing and housing affordability. And so that's a crisis we're dealing with all over the place, including here in the Pacific Northwest. I don't know whether you saw this study from the Harvard Center for Housing Studies that 41% of our rental housing nationwide is at high risk from climate change impacts. And we can see on this map that there are a lot of areas in Oregon and Washington where that's true. Flooding is one of the key risks associated with that. So at the same time, we're trying to address this housing crisis. Climate change might be undermining or eroding, literally and figuratively, our existing housing stock and taking away our ability to address that other issue. So resilient housing is going to be one of the things we need to focus on. So let's talk about water and then wind after that. And you may or may not know that floods account for 90% of the natural disasters in the US. And overall, flooding is responsible for more of the total damages in terms of loss of life, economic damage, and property loss from natural disasters. And while coastal areas are some of the areas most subject to flooding, significant flooding happens in every state in the United States. Different people have different ways of classifying this, but I want to talk about generally types of flooding. The two main ones that you need to address is fluvial or riverine flooding and pluvial or heavy rainfall flooding. One of the scenarios that's happening more and more down in Florida is sunny day flooding or tidal flooding, where sea level rise is actually pushing, sea level rise and just king tides are pushing tidal water up into drainage systems and causing flooding in streets, even on days when there's no rain around. And of course, flooding can also come from storm surge from major storms. And wind-driven heavy rainfall combined with wind or wind-driven rain can be a source of flooding in buildings. back when Hurricane Ida or the remnants of it hit New York City, there are many older buildings that weren't designed for wind-driven driving rain, and there was some significant flooding in buildings in Manhattan and elsewhere in New York from that hurricane remnants there. When we're trying to assess flooding, one of the first places that I think many of us are used to going to is FEMA flood maps. And this is, of course, a good place to start because FEMA is the primary government agency that addresses flooding and helps with identifying risks and helping with recovery. But it's important to note that FEMA flood maps only address riverine or fluvial flooding. They do not address pluvial flooding and the other types of flooding I just mentioned. So you can start with a FEMA flood map, but don't finish with it. And the other key piece, and I'll emphasize this maybe more than once, is that that FEMA flood maps are based on historic data as opposed to future climate change. And so, so they tend to underestimate flooding risks because we are having more frequent and severe rainstorms that due to climate change that will cause flooding in areas that weren't necessarily seeing it in the past. And here's just one example of a property. The upper map shows the FEMA flood map showing it in a low flood risk, this particular property in a low flood risk zone. But looking at other resources to understand pluvial flood risks, there's a significant area through the center of the site that has a flooding risk that needs to be addressed in the development. The other thing that in terms of terminology around flooding, people often get confused in terms of the terminology, whether it's referring to frequency or probability of an event happening. And this doesn't just include flooding. This can be other storms that are referred to in terms of their return period. So a storm event return period is the recurrence interval. But does a 100-year storm means that it happens more or less once every 100 years? And that's actually not correct. It means that there's a approximate 1% annual chance of an event that a probability of an event that exceeds the severity of that particular type of storm. So it's a 1% annual exceedance probability, not to say that if you had a 100-year storm event last year, that it's going to be roughly 99 years before the next one happens. So one way to put this in perspective is that 100-year storm event probability means that there's a 10% chance over a 10-year commercial real estate hold period. So the investor who might be holding that office building for 10 years has a significant chance of flooding occurring or some storm event happening. And over the course of your 30-year mortgage on your home, that's about a 26% chance of that event happening. So it's not insignificant, even though it sounds like once every 100 years or 100-year event might sound in unlikely frequency, but it's actually significant. So just to kind of put a fine point on that, return period is a statistical descriptor of severity. It estimates the probable occurrence during a given time period, and the real kicker is it's derived from historic records, so it does not take into consideration future climate change events. And just to give one example of this, this last January and February, Southern California had severe flooding because they had not just one, but 2 1,000-year atmospheric river storm events hitting the coast, causing significant flooding and landslides in the area. So that's a 1,000-year event sounds pretty rare, but 2 of them happened within a month. And FEMA provides some data on the impacts of climate risks from flooding and other hazards, and is showing that they're increasing. And this 660% increase in flood insurance claims is not insignificant in the last short period of time. The other thing that's not considered in typical flood risk things is the potential for dam failures. And while this is less of an issue and maybe not something to lose sleep over. It's certainly something to pay attention to when assessing potential flooding risks. The 95% of the dams in the US are privately owned, and 30% of those are classified as high or significant hazard potential. And some of you may remember the 2017 spillway failure in Oroville Dam in California. That thankfully it did not result in a disaster, but it was threatening tens of thousands of homes in that area of California. So we need to be cognizant of that. And just to put this in a more local perspective, here's a map. Each one of those blue dots represents a dam in Oregon. Not all of those are high hazard. Not all of them are significant, but there's a lot of dams around our state. And statistically speaking, some of them might be at risk of failure and significant. And just to pull out one example, the Hills Creek Dam in Oak Ridge, Oregon, while its failure is unlikely, if it did fail, it would flood parts of Eugene and Springfield with 15 to 35 feet of water. So, something to consider in thinking about hazards. So I'm going to shift gears and get into some terminology around flooding and flood-resistant design in buildings to give you some tools to take away in thinking about this. And a couple of basic ones is understanding that base flood in elevation, or BFE, refers to the height of a potential flood risk. In the case of riverine flooding, this is typically determined by FEMA, but one also needs to look for data on base flood elevation for things like king tides in the case of coastal properties, or storm surge from hurricanes or other type events. So base flood elevation could vary, but it's where we start with understanding. And then, of course, design flood elevation, or DFE, refers to the elevation of our lowest floor of the building. And typically we want this to be at least 1 foot and maybe more above the base flood elevation to provide some freeboard, so that there's some space between the highest floodwaters and the lowest floor of our buildings. When we want to talk about flood mitigation, there's some terminology in terms of the types of flood proofing we might do. I personally don't like the word flood proofing because it implies that it's going to take care of everything and there's no issue. I prefer flood resistance, but flood proofing is the terminology that's used, so I'm going to stick with that term here. Flood proofing can be either wet flood proofing or dry flood proofing, and I'll just describe those in a moment, but it might seem obvious. And then flood proofing can also be active or passive in terms of requiring active deployment or being passively deployed. And I'll explain those in a little bit more detail. While lingering on this slide for a moment, I don't know if you've heard of the Waffle House rule, but FEMA officials use that because Waffle House in the Southeast United States in particular is famous for being open all the time and prepared. And so if a FEMA official arrives after a hazard event has happened and the Waffle House is closed, then they know it's a very severe disaster. So when we talk about wet flood proofing, flood proofing is designing the building to allow water to flow through the lowest levels of the building and putting flood vents on that lowest level. This allows the water to move through as opposed to moving around and providing scouring at the foundation or putting pressure on the walls of the building and pushing it off its foundations. So it avoids catastrophic damage to the building, and is less expensive to implement generally than dry flood proofing, but it also requires a more extensive cleanup because those floodwaters, of course, are going to be filled with mud and debris and such, and require some cleanup. So that in wet flood proofing, in addition to flood vents, you also need to design the structure and interior finishes to be resistant to flood damage. And let me be more specific about this. In the case of wood framing, this would mean using pressure treated studs as opposed to ordinary wood, using closed cell insulation instead of batt insulation, creating a break in the gypsum board on the inside to prevent moisture from wicking up the entire wall and then becoming a spot for mold growth. So limiting that flood damage to the lower portion, or thinking about more moisture resistant materials like the CMU block and tile and other materials that don't absorb water and can be cleaned afterwards. Dry flood proofing is when we place the flood barrier at the exterior wall and prevent water from entering the structure. This is a more expensive way to build, but it also limits the damage from the flood. The key piece here is that the exterior walls then have to be designed to manage the hydrostatic pressure of standing water against the wall at whatever height it's expected to be in a flood, as well as dynamic pressure from the flowing water and floating debris like automobiles that might collide with your building during the flood event. So there's some important structural and waterproofing considerations in designing for dry flood proofing of a building, but it certainly is less messy to clean up afterwards. Dry flood proofing can also be achieved with permanent or temporary flood barriers that surround the building, so you keep the water away from the building and then avoid those issues. So you have those permanent or temporary barriers to keep the flooding away. The key piece here is that you still might have rainfall falling on the roof of the building and the site adjacent to the building. And so it's critical to have auxiliary pumps on backup power that can remove that water, so prevent a bathtub from occurring inside your flood barrier while you're trying to keep water away. The other terminology I mentioned is about active versus passive flood proofing systems. Active systems require storage space on site to keep these materials when a flood's not happening, and they also require manual deployment. So you have a staff available to unpack and deploy these systems before a flood happens. So in this case, there's a disadvantage that in a flash flood situation, you don't have time and warning to get the flood barriers out. And it's critical that people aren't scratching their head at the time of critical nature. So the staff who will be responsible for that need to have regular training on the deployment of those systems. Those active systems could be things like what they call flood logs, that are these planks that fit into mounting brackets at the edge of windows to prevent floodwater from entering at windows and doors on the building, or they can be temporary barriers that are set up away from the building. Passive systems, by contrast, are either permanent or automatically deploy in a flood event, so you don't need to have the storage space and training. These are things like pop-up barriers at parking lot entrances or pedestrian gates to structures, so that they pop up in the case when water gets close, or they can be at the building, active or passive systems like water flood-proofed curtain wall systems that are now available to install on lower floors of a building that hold back floodwaters and resist impacts from floating debris. The key piece here is that these systems, you don't want to find out that they're not working at the time of the flood events. So regular maintenance and testing is required to make sure that they're ready to operate in the event of a flood. The other key piece with flood resilience is elevating electrical and mechanical equipment above the design flood elevation, so that the systems still operate afterwards, and looking at things like flood proofing of elevator machine rooms that tend to be on lower floors of buildings. In some cases, elements of a water supply might be subject to contamination in a flood event. So making sure that those are adequately protected and having sewer backflow valves to prevent sewage backup into the lower levels of the building. I will not go into detail on all the standards, but American Society of Civil Engineering, FEMA, and ANSI all have various standards for design and testing of various different floodproofing elements on buildings. And so these are elements that can be incorporated into your specifications and used for guides in designing floodproofing in buildings. And just quickly noting in some specifics, the LEED version 5 will have a resilient site design prerequisite that requires flood resilience for critical facilities like water and sewer and utility supplies. And it is incorporating an optional enhanced site resilience credit that looks at designing for resilience for some of the primary hazards that I identified, things like flooding or high wind or extreme heat. So let's move on to talk about wind. A few interesting things. I don't know if you knew that 75% of the tornadoes in the world occur in the US. And so they're significantly, and a lot of them obviously are in Hurricane Alley in the center of the country. Unfortunately, for people in Mississippi, Alabama, Tennessee, and Kentucky, and other places, the Hurricane Alley is migrating eastward and expanding, so that more areas of the central part of this country are being subject to more frequent tornadoes. Also, while climate change so far has not necessarily increased the number of hurricanes we have on average, since 1980, the proportion of Category 3 and higher hurricanes in the Atlantic has doubled, and this is likely due to climate change and warming waters. But windstorms that we need to deal with in terms of resilience fall into a few categories, and we all know about hurricanes and tornadoes. A derecho is a straight line winds that come from a similar source to what causes a tornado in terms of downdraft winds, but instead of being cyclonic, they result in a band of strong winds going straight across the land. Houston actually experienced a derecho this last spring. It broke out windows in many of the office buildings in downtown Houston. And unfortunately, then a month or so later, they experienced a hurricane that caused similar damage. So they got hit twice by two different types of windstorms. Straight line winds are more of the what we're used to here in the Pacific Northwest, with the winds associated with the barrier boundary between high and low pressure weather systems. And then a haboob is also known as a dust storm. It also comes from thunderstorm activity and downdraft winds, but is accompanied by a wall of dust. And least you think that Pacific Northwest is immune from tornadoes just because they mostly happen in the Midwest. We have had a not insignificant number of tornadoes in this region over the last half century, and including some of you may remember in 2016, there was a EF2 tornado that hit Manzanita and caused significant damage there. When we talk about wind in general, we can look at several resources to identify where risks are. FEMA maintains the National Risk Index and provides this wind risk map that generally coincides with things like Tornado Alley. But we have some lesser but important wind risks here in the United States. I mean, in the Pacific Northwest, and some of those have been getting worse. The key element that many of you might be familiar with already is the ASCE's 7 standard, which talks about wind zones and design wind speeds for locations. The key thing I want to emphasize here is this is going back to the code comment. This is design wind speeds that are a minimum standard for a location, and perhaps because of changing conditions and greater severity of events, it's prudent for us to be thinking about designing for higher wind speeds than the minimums identified in ASCE 7. When we think about vulnerabilities on a particular building to winds, we need to understand where the wind pressure zones are, and this is generally at soffits, edges, corners, and ridges of roofs, or the primary areas of vulnerability. And a key element there is that when a failure happens at one of those locations, it then cascades and causes a greater failure across the entire roof system. ASCE 7 identifies those wind pressure zones for different roof types and structures, and also identifies where those pressure zones are on buildings. So focusing on those edge and corner zones is a critical piece, and I'll come back to specifics on that in a moment. In terms of designing for wind resilience, thinking about some basic things like taping panel joints on roof sheathing, especially like in wood frame construction. A key element here is this reduces the risk of wind pressure pulling at the joints between those panels and causing sheathing failure. And if the roof above the sheathing fails, then the sheathing and the tape then act as a secondary roof to prevent moisture from getting in the building in significant quantities. But better still, one of the strategies that I like is looking at self-adhered membrane roof underlayment, so that you have a second roof. If there's a failure in the primary roof system, you've got a second means of keeping moisture out of the building, which compounds the impact of wind with water and it creates significantly more damage in the structure. But a key piece in that, going back to those wind pressure zones that we just talked about, is upgrading roof attachment systems in those high wind pressure zones. So instead of going with minimum spacing of attachments, thinking about closer spacing of attachments in those high wind pressure zones, so that you reduce the potential for a cladding failure. And one final note on roofing and cladding is that soffits are one of those weak points, and so reinforced soffit cladding is critical. One of the other key points of failure in wind events is openings, and a key element of that, similar to us talking about active versus passive systems for floodproofing, we can also think about active and passive systems for opening protection. Impact resistant glass is a passive system that will prevent flying objects from destroying, breaking through glass and causing a failure in the entire building enclosure. They may break, but they'll prevent more catastrophic loss. But in the absence of impact-resistant glass, storm shutters that can be deployed in advance of a forecast wind event are a good way to protect those openings. It's important also to think about vents and grills on the outside of a building, because they're a source of both failure as well as wind-blown rain pushing water into a building. So considering resilience in terms of the placement and specification of those, and especially in residential construction, garage doors are a key point of weakness. Many houses that are destroyed in tornadoes and some hurricanes happen because the garage door fails first, and then the house gets pressurized and the roof gets blown off. So having reinforced garage doors is the key resilience element for wind. In terms of structures, ensuring that you have a continuous load path to tie together the structure from roof to foundation to resist those uplift pressures from wind. And then not forgetting about equipment, roof-mounted equipment that could both blow away, which is difficult for the building itself to function later, but also those equipment can then damage other elements of the building. So having reinforced tie downs of equipment on the roof. Another key element is that, especially when it comes to things like tornadoes, it's possible to design buildings to resist, EF 1, it was 0, 1, and 2 tornadoes, but it's difficult to design for an impact of an EF 3 or higher. But we still want to keep the people inside the building safe. So designing safe rooms is an important element, and FEMA has some standards for designing those safe rooms. But in the absence of the ability to put in a safe room, FEMA also has their BARA standard, the best area of refuge. And this is the thing to consider when an owner is not necessarily ready to jump into designing a full safe room in a high wind hazard zone. Making a area of refuge is a critical safety feature. Just to kind of close out this section, LEED version 5 is including a resilient spaces credit, which talks about various different building hazards, and a couple of them that are included in this as options if these hazards are present is designing safe rooms or areas of refuge for high wind events. And then harking back to our discussion of earthquakes last week, going beyond the structural resilience for earthquakes, and also making sure that furniture, equipment, and other things are not obstructing egress. Finally, I wanted to close out and talk very briefly about heat and leave still some time for answering any questions. Extreme heat is a significant hazard that is increasing. Extreme heat actually kills more people globally than any other weather-related disaster, and the frequency, intensity, and duration of heat waves has been steadily increasing since the 1960s. And we all remember our heat dome here in 2021. And last summer, we were spared, but much of the rest of the country experienced extreme heat for extended periods of time. So significant impacts on much of this country and the rest of the world. When we want to think about designing for thermal resilience, it's pretty self-explanatory, but measures like cool roofs or vegetated roofs help to make our buildings more thermally resilient. A big element is enhanced enclosure design, so higher insulation values and lower infiltration, or simply put, designing with passive house standards in mind is an important element of thermal resilience. Of course, exterior shading to prevent heat from entering through windows, designing to allow for passive ventilation and night flushing so we can cool off structures at night, and designing for tree shading and reducing paving and reflective and using reflective paving. So I think a critical element here, going back to my discussion about multi-hazards at the beginning, extreme heat often coincides with power outages, and so we can't just say we're going to install more air conditioning to deal with that. We need to design for thermal resilience till we reduce reliance on air conditioning and can be thermally resilient in a heat wave combined with a power outage. I want to quickly note, thanks to Bora Architects and Tui Lee and Corey Squire with Bora, who produced this really insightful study about thermal resilience, focused on a multifamily housing project, and tying it back to the heat dome in 2021. They looked at thermal resilience and in 3 different scenarios: a baseline scenario with a standard code compliant building and no occupant engagement around night ventilation. What was the impact of an engaged occupant on thermal resilience? And then finally, using advanced construction of passive house standards plus an engaged occupant. And the results are pretty striking. You can see the spikes in heat from that heat dome that happened, and how the indoor conditions were at elevated and dangerous levels for not just during the heat wave, but for 4 days afterwards, because of the building not cooling off. Whereas if the occupants were instructed on how to lower blinds during the day and open windows at night, we reduced that impact in the danger zone down to just 3 days during the heat wave. But then if we went further and used passive house standards as well as night flushing, we only reached the sort of danger zone of temperature for part of 1 day. So a significant impact in building thermal resilience. In a final note on this, LEED version 5 is incorporating some other resilience-based requirements, looking at management modes for wildfire smoke, management modes for extreme heat and cold events, and operable windows for also for extreme heat events and power outages. So I just want to close our discussion talking about our duty as architects. We have an important role to play in terms of designing for resilience. And I think many of you might know that it's now part of the architect's standard of care to inform our clients about the impacts of climate risk on the projects we design for them. And the AIA has developed some really important resources, including developing our code of ethics and professional contact, developing the resilience product process guide. And here's a critical resource: the hazard and climate risk user guide that includes some acknowledgement forms that you can use for your clients to inform them about climate risks and have them acknowledge that they heard that, whether they ask you to design to it or not. The HGA architects produced an interesting study last year that was published, showing that not enough architects are actually paying attention to climate projections in their designs. The AIA, with the help of HKS architects, developed the Resilience Design Toolkit that was released last year, and it provides a great step-by-step discussion of how you can take your project teams and the owner through resilience from start to finish on a project. So just to close, sustainability and resilience go hand in hand, and we need to be thinking about both of them. And resilience is your responsibility as the architect for the projects you design. So with that, I'm happy to take questions.
Alan, can you see the chat, or do you want me to read what's in the chat?
I can't see it right now with my view. I can stop sharing and probably shift my screen, but if you can read to me, that would be great.
First, I want to say for those who need to leave at 1, that you can feel free to contact Alan if you want to put your, I can guess, if you want to put your name in the chat, your email. But we can stay on for a few more minutes for those who are able to do that. The first question was, would you consider unvented conditioned attics a mitigation to hazard risk for wind, fire, and heat? And if so, does that translate to conditioned crawl spaces as well?
I guess I will answer, it depends. Generally, I think that would be true, because a vented attic would allow wind pressure issues to enter, and as well as wildfire embers and other things. And so those conditioned or semi-conditioned attics and crawl spaces might tend to be more resilient than having them open and subject to wind and fire and water and other elements. But I don't know that that's always the case.
Okay, I've added your email, so you don't need to do that.
Oh, thank you. And I shut off before my last slide that had my contact information.
People are just saying thanks, an awesome presentation. The recordings will be available, Sarah. I will get them up on our AIA Oregon.org website under program archives. There's one from Sophia Suhu. Do you expect Oregon, Washington to adopt NOA number for envelope products like Florida Building Code is requiring?
I can't speak specifically to whether or not they adopt those, but I do suggest that that some elements of building codes like the Florida Building Code for wind would be appropriate, because we are seeing increased wind events here. I can't speak to whether or not Oregon code will adopt that, but I do think that there might be situations in high wind risk zones where we should be voluntarily adopting some of those standards.
Okay, lots of thank yous. Do you have any suggestions for working with clients, property managers who might be reluctant to spend on resilience measures beyond code minimum and or put in the effort to educate and manage occupants?
My main suggestion, I think that the some of the resources that AIA has in terms of resilient project guides are a good source. That they have some other resources that you can use with clients. So that's a place I would start with, and I'll just share watch this space as well, that the AIA Resilience and Adaptation Advisory Group is working on a resilience toolkit for architects that's going to actually walk through the assessment and communication process. So we will be coming up with more resources, but some of the ones we already have, the toolkits that are available, are a great place to start with that. And I think that the key piece is to communicate that that whether or not they're thinking about them, in the case of a private development, the institutional investors who are going to be buying that project at some point in the near future are looking at that and will be valuing projects differently if they have greater risk.
Will you be able to share the links to those toolkits that you're talking about?
Yes, I guess I should have had those right at hand. Kathy, maybe there's a way I can follow up with that to participants.
You were going to send me your slides.
Yeah, so what I'll do is I'll add that into the slide deck.
Okay, that will work.
Although I just saw somebody drop that in, somebody else dropped that into the chat already. So
thanks, Nir.
Oh yeah, Nir, thank you.
All right. Well, I don't see any more, and we have gone about 5 minutes over. So unless
sorry about that.
Oh, no worries, no worries. Unless there's any other questions, we'll say goodbye for today, and remember to show up for next Friday. Got our fire resilience coming up.
Thank you, Alan. Thank you all.
There's somebody just said something about links to Jay Raskin's presentation. They are on our website right now, just so everyone knows, and that will be in the same place under our program archives under events. All right, bye everyone.
Bye-bye.